So welcome back. Today we are discussing about water requirements of crops. Okay. So how much water do they need and how do they acquire it and what are the ways to calculate other things. That is our main concern. Okay. So our first topic is how do we classify the water present in soil. We can classify the water present in soil into three. Okay. Water soil, water present in soil can be classified into three. First one, hydroscopic water. Okay, suppose we are taking a sample of soil and we are keeping it in an oven and heating it till all the moisture disappears. It is dry as it can be at its maximum level. Okay. So we are taking a sample and keeping it in oven and heating it till the moisture in it is completely vanished. Then we are taking it out and keeping it in a beaker in our table. At that point on, the soil will be acquiring some moisture from the atmosphere into the soil. Okay. That part of water is called hydroscopic water. It cannot be taken otherwise. Okay. So the moisture that is acquired by an oven dried sample when exposed to atmosphere is called hydroscopic water. Okay, that is a minute type of water content in soil. So it will be the lesser kind, hydroscopic water. Second one is capillary water. We all know the meaning of it. Capillary water, obviously, as we know, it is a water present in the water between the capillary holes of soil. With respect to our topic, it is the water in soil in excess of hydroscopic water which is present in the capillary holes of soil. Okay, so it will be the water which is in excess of hydroscopic water and it will be in capillary holes. Okay, so that is capillary water. And the last one, gravitational water. And gravitational water is the water in excess of hydroscopic and capillary water which can be drained by gravity. Okay, if suppose there is a pressure difference or elevation difference, this water will be flowing away. Okay, so gravitational water is the type of water in soil, present in soil in excess of hydroscopic water and capillary water which can flow in the presence of gravity. Okay, so obviously when you are watering a plant, if suppose if you are watering a tree or a plant, gravitational water will not be reaching into the roots. If this is the roots, gravitational water will not be reaching the roots. It will be flowing away. Okay, hydroscopic water will be very hard for the roots to acquire. Okay, so the main portion of water will be acquired by the roots or the plants will be capillary water. Okay, keep that in mind. That is important. Okay, that was water classification of water present in soil, hydroscopic, capillary and gravitational water. Okay, so now we move on to soil moisture constants. First one, saturation capacity. This can also be called as maximum moisture holding capacity or total capacity. It is the amount of water required to fill all the pore spaces between soil particles by replacing all the air. and it is the upper limit of possible moisture content. That means it is the moisture content when the soil is immersed in water. When flooding happens, this will be the moisture content. Saturation, okay, that is saturation capacity of soil. Second one, field capacity. This one is really important. Field capacity is the moisture content of soil after free drainage has removed most of the gravity water. That is, after irrigation, most of the water that we irrigated flows or drains through the soil before it can be consumed by the roots or plants. Okay, so after this, field capacity is important, because field capacity is the upper limit of moisture content that can be acquired by roots. If suppose field capacity is 30% or 40%, that 40% is the maximum limit of water that can be stored in that particular soil that can be effectively taken up by a plant. Okay. Here there is saturation at the most top point of moisture content, and field capacity, that is the upper limit of useful water. Okay. Third one, permanent wilting point, WC. It is that water content at which plants can no longer extract sufficient water from soil for its growth. The permanent wilting point is at the lower end of available moisture range. Okay, if suppose the permanent wilting point is 10%, if the moisture content of that soil goes below 10%, the roots cannot acquire water from the soil. It's that simple. Okay, so permanent wilting point is the lowest point or low point of moisture content below which roots cannot acquire water for its growth. So wilting means a temporary death of a plant. It stunts its growth and it stops growing. And we all know what wilting is. If you don't water a plant, what happens to a plant? That is wilting. Okay, and there are two kinds of wilting: temporary wilting and ultimate wilting, other than permanent wilting. Temporary wilting is the wilting that takes place in a hot day for a plant. Okay, suppose on a hot day at afternoon 12 o'clock, your plant may wilt slightly, but at night it will regain turgidity. Okay, that is temporary wilting. Ultimate wilting is slightly different from permanent wilting. When ultimate wilting occurs, the plant will die eventually, even if you pour in water. In permanent wilting, if you pour in water, it will regain its life, but in ultimate wilting point, it will not regain its life. It will be died soon. Next two slides are important to understand. Available moisture. It is a difference in water content of soil between field capacity and permanent wilting point. Okay, so available water, as the name signifies, is the available water for the roots to take it up or for the plants to take it up. So that will be the difference of moisture content between field capacity, which is upper limit, and wilting point, permanent wilting point as the lower point, as it is shown in the figure. Then what is readily available moisture? It is the moisture content that can be easily or readily available for the roots. It will not be any hardship for the roots or the plants to take it. It will be very easy. Okay, it is the portion of available moisture that is most easily extracted by plants, and it is approximately 75% of the available moisture, and it is top 75% as it is shown in the right side of the figure. Okay, readily available moisture will be 75% of available moisture. Moisture equivalent. It is the percentage of moisture retained in a small sample of wet soil 1 centimeter deep when subjected to a centrifugal force 1000 times as great as gravity, usually for a period of 30 minutes. Okay, and so there are some equivalent equations for that. Just read through. Last one, last constant, soil moisture deficiency. It is the water required to bring the soil moisture content of soil to its field capacity. Okay, if suppose field capacity is 40% and right now your moisture content is just 20%, then this constant will be 20% more. Okay, you have 20% now. To reach the 40% field capacity, you have to apply more 20% more. So 20% will be the deficiency, moisture deficiency. So next topic is limiting soil moisture conditions. Suppose we are trying on a graph like this, in which y-axis is rate of growth of plants. Rate of growth of plants. We are pouring water for growing of plants, obviously. And x-axis, it is moisture content of soil. Okay. So we are trying to analyze how these two relate. How does moisture content of soil relate to rate of growth of plants, for which we are doing irrigation. Okay. So as we know, FC, field capacity, one of the soil constants, soil moisture constants, field capacity is the limit of, upper limit of moisture content for irrigation. If we are doing irrigation, we are pouring water, we will be filling up water till FC. If suppose for a crop or a soil, FC is, field capacity is 40%, we will only be filling water up to 40%. That is enough. That is FC. Okay, and that is FC. So for every watering, if FC is known, we will be filling water till FC only, field capacity only. It is the higher limit of moisture content that can be used by plants. More than that will be drained by what? Gravity. Will be drained by gravity. So till FC we can use, plants can use. So FC, if suppose FC is 40%, it won't be 40% always. If suppose it is 40%, we will be filling the water till 40% only. Okay, so FC will be the last end, right hand end of this graph of moisture content. Everything else will be irrelevant with rate of growth. Okay, so FC will be here, the upper point, and there will be this, suppose this line will be wilting point. From below that, the plant may wilt off, plant may die, permanent wilting or ultimate wilting. So this point, from this point, irrigation starts, and at field capacity irrigation ends. If suppose wilting point is 10%, 10%, this portion of water only will be taken up by the plants. That's it. Nothing below, nothing over than that. Okay. So wilting point, that will be a percentage, and as per studies, rate of growth will have an optimum value for a particular moisture content of soil. Okay, and the rate of growth as we study it will be something like this. Okay, it won't be maximum in melting point. It will be very hard to pump up for the roots of water, roots for take up water, and it will not be maximum rate of growth at field capacity either. There will be an optimum point, and it is termed as optimum water content or moisture content. Optimum water content or moisture content at this point. Okay, and as we know, this portion is known as available moisture. This portion, available moisture. Okay, and as we know, readily available moisture is 75% of available moisture. Okay, so readily available moisture is 75% of available moisture. So that will be from 75% we can take from wilting point or field capacity. Okay, so obviously it will be taken from field capacity, because if suppose this is M0, point M0, and M0 is lower limit of readily available moisture. Okay, so this will be FC, from M0 to FC will be readily available moisture. Okay, because the reason for finding readily available moisture is this portion, M0 to wilting point portion of water will be very hard for the roots to pull up. It will be very hard for the roots to pull up. It will be easier for the plants to pull up this portion, that is readily available moisture portion, that is FC to M0 portion, to pull up the plant for the roots. Okay, so we consider readily available moisture for irrigation purposes, and that will be 75% of FC to WC. Okay, so in this graph it will be something like this: 75%. This will be readily available moisture. Okay, I hope you get it. There are two kinds of available moisture: available moisture and readily available moisture. Readily available moisture will be 75% of available moisture. It is available moisture 75% of upper 75% of available moisture. Okay, and M0 is taken as lower limit of readily available moisture. Okay, then we are moving on to the next topic: depth of irrigation and frequency of irrigation. Depth and frequency of irrigation. Okay, so another graph we are trying out. In this, x axis is time and y axis is moisture content of soil. Okay, so it is based on irrigation. How do we irrigate water? Okay, so the moisture content previously we had drawn in x axis, now we are drawing it on y axis. Obviously there will be FC in here, wilting constant in here, and M0 in here. Okay, available moisture, readily available moisture. Okay, I hope you understand. FC, WC to FC is available moisture, M0 to FC is readily available moisture. Okay, so while watering we will be filling up. If this is FC, this is M0. Okay, while watering or while irrigation we will be filling water till FC. Then as the time progresses, 2 hour, 3 hour, 4 hour, etc., as the time progresses, this water will be taken up by the plants, by the trees, and thus the moisture content will be lowering like this. And when it reaches M0, the lower limit of readily available moisture, we will again water it. We will pour water into the field and then suddenly it increases to FC. Okay, then as the time goes on, it will again lower and lower, and then again when it reaches M0, we will again water it. So the cycle will be continued. Okay, so this is the pattern of irrigation in a field. We will be keeping it in readily available moisture inside M0 and FC. Okay, so now we are going to calculate, or we are going to find an equation to find out frequency of irrigation. How frequently should you irrigate water, or should you pour water into the field? Okay, so there is an equation for dW, and dW is the depth of water. If depth of water is 1 centimeter, we should add 1 centimeter of water, thickness water, to the whole field. If 1 acre of land is there, you should add the water of 1 acre of area till it fills 1 centimeter of water, thickness, depth. Okay, so dW is given by gamma D by gamma W into D into FC. This part is important. FC minus M0. Okay, where dW is depth of water, gamma D is dry unit weight of soil, gamma W is unit weight of water, D is depth of root zone, FC is field capacity, and M0 is, as you know, lower limit of readily available moisture. Okay, D, depth of root zone, is the depth up to which the root of the plant is reached. We suppose for a paddy field it may be 50 centimeters. That means the roots will be reached till 50 centimeter of depth. That is D. Okay, that will be different for different crops. For a tree it will be much bigger. For a plant like paddy, wheat, etc., it will be much smaller. Okay, and it will be in meters when you substitute in this equation. So dW is equal to gamma D by gamma W, D into FC minus M0, and this part is important because this part, when you do numerical part, FC minus M0, this part will be changing, especially M0 part. If suppose the question is to find available moisture, this M0 will be changed to WC. Okay, right now we are calculating everything on the basis of readily available moisture. So the upper end is FC and lower end is M0. If the question is on only available moisture, upper limit will be FC as always minus, instead of M0 it will be WC. Okay, so the concept should be clear. Okay, this portion will be changing according to a question in your numerical problem. Okay, so keep in mind the formation gamma D by gamma W into D into FC minus M0. Okay, and for finding frequency of watering, that is FW, frequency of watering, the equation is given as, we suppose dW is given by, or dW, the depth of water we are pouring into the field, we suppose it is 10 centimeters. Okay, or 100 centimeters. if the amount of water you are pouring at a single irrigation cycle. If suppose on Monday we are pouring in 100 centimeter of water into the field. Suppose it's a very big value. Suppose you are pouring in 100 centimeter of water into the field on Monday, and on daily basis there will be, suppose there will be 10 centimeter of decrease, 10 centimeter of consumptive use of water by the crop. Suppose you are using paddy, on Monday you are pouring 100 centimeters, and on each day there is a consumption of 10 centimeters. So obviously after how many days you should be watering again? After 100 by 10 days. Okay, I hope you understand. For one time watering we are using 10 centimeter of water, 100 centimeter of water, 100 centimeter of water. In that 100 centimeter, 10 centimeter is used on Monday, 10 centimeter is used on Tuesday, 10 centimeter is used on Wednesday, etc. So it takes 10 days to empty this supply of water that we did on Monday. So next watering should be after 10 days, 100 by 10. The equation is, remember the equation, just the equation, dW by Cu, where dW is depth of water and Cu is daily consumptive use of water by the crop. Any crop, it will be different for different crops. For sugarcane it will be much higher, for a mango tree it will be much lower. Cu is daily consumptive use of water, dW is what we got, depth of water, and Fw is the frequency of water. Okay, so I hope you understand, and now we will move on to numerical problems. And understand theory and thorough it, you will need the understanding more than the equations in solving numerical problems. Okay, thank you.